Okay, well, I owe you guys a lot of homework, and now, oh well, we're taking this. Oh, this is this is statics. So I also owe you a quiz in thermo. I'll owe you a quiz after today, but that is a high priority for me now. I have time to do this stuff, so that those grades will start coming in. But yeah, I'm sorry I've gotten behind. I know it's definitely helpful to get feedback immediately. So hopefully, once I get caught up here, things will be back to sort of normal with that. Anybody have any homework questions before I get into new stuff?
I didn't think we had an assignment.
Oh, okay.
I had a question. One of the things we were working on had like a different number of equations and variables.
Oh, yes. That was that caliper thing, right?
Yes.
Okay, yes.
It was the
The rangeur, the sort of medical pliers
I
thing.
remember writing it. I think I have to read
Another thing I heard.
Yeah.
What I noticed in that one, you could just literally take the proportions of the lever arc to find out the output of because it was a 5-to-1, and then or no 10-to-1, and then it was 5-to-1, and that's 50 times 10 is 500 times 5 is 2,500.
Mm-hmm.
Can you just eyeball the lever arm proportions?
Well, I mean, that's sort of, I mean, for that specific question, yes, you could have done that, but really what you're trying to get is just practice with this method, and to calculate those intermediate forces. I mean, like if you're using this as an engineer of that device or whatever, you want to know those reaction forces too, So yes, the short answer is yes, but really I think what you want to do is just keep getting practice with the approach.
The point of this is to figure out what kind of fasteners you need to use, because there's going to be force on those fasteners.
Yeah, right.
Yeah, that's clever.
Brakes.
It's clever to look at the
Yes.
statics problem and then use a completely different idea. 'Cause
Yeah.
my mind was only thinking.
Yeah, right.
Statics.
Well, let's think about this for a second. So you got like that and that, I think. And then do you think there's a way to flip this? That would be so amazing.
Yeah. So the top middle one, drag down on that one.
Ooh, there. That worked. Okay. Oh no, they don't meet. Well, it's like that, and there's four members, and what you end up with is 9 variables. So you have 4 bodies. So you get 12 equations. You get 9 variables. And so the answer is, because of symmetry, you can just choose any 3 of those 4 bodies and come up with the equations for those and solve the problem.
So we have duplicate equations?
Yes, that's right.
Because of symmetry. So it wasn't clear when looking at them.
Right.
But they are.
Right.
Okay. So in my calculator, the simultaneous equation solver, I did 12 equations, 9 variables.
Right.
And it just sort of worked.
Oh, that's interesting to know. I mean, yeah, if you have a statically determinate system and you get more equations than variables, you can just drop 3 of those equations and it'll work.
Does that be a specific 3 though?
I have never, I have never just dropped 3, and I suppose if there's a chance it wouldn't work. I could imagine, if I'm thinking about it right, then just put one back and drop a different one. But I've never had it not work by just dropping any 3 equations.
So you just pick a body, then drop one of the bodies.
Yeah. I mean, if it comes out even like that, 9 variables, so that's a factor of 3, you know, so yeah, then you can just drop one of the bodies.
If you drop a body that has variables, then we just not get answers for those.
Well, the fact that you have more equations than variables means that those have to be in other equations
okay,
too.
Right.
Yeah.
Okay, cool.
Any other structures questions? So I wanted to just go through structures number 5, and just show how you could do this problem, making the truss assumption. And I want to say, in this class, don't do anything with the truss. I mean, if you want to, you can. But my recommendation is don't do anything with the truss assumption. I'm just showing it to you for if it comes up in future classes. That's all. Okay. So here's what it looks like. And all of these are pin joints. And let's call it members 1, 2, 3, 4, 5. And I'll call this A, B, C, D, and E. Well, we can, so what are the 2 force members and what are not 2 force members? The only ones that aren't 2 force members are 1 and 4. Okay. So we can assume that we can treat the joints A, B, and D like the pins are part of member 1. And we can treat the joints C and E as parts of member 4. So let's start isolating members to start with. The only members that we're going to isolate are members 1 and 4. And then let's see what we have. But notice that all these forces, like on any body that they connect to. So the member 2 connects to member 1 and connects to body 4. We're going to assume that that's just like a cable in tension. It can also get positive or negative answers. That's the difference between it and a cable, but we're going to treat it like it's a cable. So a free body diagram of member 1 would look like this. You have a force RA, and a couple MA. And then at the midpoint, the member 2 connects to that. We're going to assume that that's a cable tension, so I'm going to treat that, I'm going to call that F2. And then at D, we have 2 things connected to it that we're going to treat like these plus minus cables, these cables that can also provide compressive force, 3 and 5. And from the trigonometry, we can figure out those directions. So there's F3, there's F5. Okay? And so this is 3 equations and 1, 2, 3, 4, 5, 6 variables. And then we'll go to member 4. That has the distributed load. I'll call that FD for distributed load. And then at C, there is a force F2 that by default we'll assume that's like a cable tension. And F3. And then the only other force on 4, so there's 2 and 3, and then there's 5 acting on the other end. This isn't something we're calculating. That's something we know. We're given that. And so we haven't added any new variables, and we have a total of 6 equations for 6 variables. These variables are RA, X and Y, MA, and then F2, F3, and F5. Bless you. And you're done with the problem once you do that. So that's a huge improvement, over the way that I made you do it. And in this class, the way we're going to do all problems, where you just know you're going to have 3 equations for every body you have. So a system of 15 equations for 15 variables. So if you spot that and you feel adventurous, you can take advantage of that. But if you don't spot it and you have time, then no problem. You can just use the full approach and it works for everything. Any questions about this simplified version? So the thing is, if these were cables, when you calculated, when you solved this, if you got any negative values, something went wrong, because cables can't provide a compressive force. But in this case, plus, minus, it doesn't matter. Yeah.
So in this approach, you don't even need to draw free body diagrams for any body that only has 2 variables?
For any body that only has 2 forces, you don't have to draw a free body diagram, because there's only one variable that you need to represent that whole body. Because like, if you think about like let's think about member 3. Okay, I mean okay, so there are 2 possibilities for external loads on member 3. There's this or this. So you only need the one equation. And you can get that by just treating it like it's a cable. So yeah, no reason to draw a free body diagram. You're not doing, basically like you're not doing a rigid body analysis on it because we already did a rigid body analysis of two force bodies in general. And what we saw is that they have to be in pure tension or pure compression.
Right, and we don't draw free body diagrams for cables either.
Right, yeah. Yeah, if you were given this problem and these were drawn as cables, you wouldn't think of drawing free body diagrams for them.
And then as soon as you throw a weight in, like you say, like up the beam weight this much, then that gets the cable.
Yep, you can't do it then. Right. So that's why this approach isn't very useful anymore in the computer age, you know. It used to be a really clever way to get reasonable answers for things that would be very hard to solve by hand or just super time consuming, you know. I wouldn't bring it up at all, except that it might come up in later classes in some assignment in passing or whatever. Here's a truss, do this, you know. Any other questions about that? Okay. So this has come up from time to time, but now we're going to start getting into the question, will something break and how will it start to break? Where will it start to break? And so the next topic is internal loads in beams. And this is the starting point for talking about stress and strain, which is what deform, or otherwise known as mechanics of materials, is all about. And so I'm sure a lot of you guys are probably taking that class in the spring. This is kind of the starting point of that. Okay, so first, what's a beam? Remember that a beam is a long, slender body with forces besides axial forces. Okay, so a two-force body like this is not a beam technically because it doesn't have off-axis forces acting that are going to tend to bend it and deform it, you know. So a beam is something that has to support these forces that'll make it bend in different spots and stuff like that.
Straight up and down. Like, would that still be considered a beam, even though it would look like the left?
If something like this had forces that weren't all axial like this, then that would be a beam.
Okay, but if it's just like straight up and down, like getting smushed like a can?
Just smushed, it would not be considered a beam, right? That would be a column, and we'll talk about that in deform. But really, remember that it's not the orientation. The orientation of the thing doesn't have anything to do with anything except how we're used to visualizing it. You could have column problems on something that's being smushed horizontally or diagonally. A beam could be any orientation. It's just that when we think about it, when we start treating it mathematically, we're going to look at from a perspective where it looks horizontal, but beams don't have to be horizontal. You just sometimes have to turn your head a little, you know. Okay, so what's the motivation for calculating internal loads? So imagine holding like a pencil or a stick between your two hands and flexing it. If you flex it hard enough, eventually it'll break. Um, okay, well, where is this stick gonna break? So let's think of a free body diagram of this stick. Well, let's say that the fingers are pulling down on it like this. The thumb is pushing up like this. That's happening on the other side too. You could calculate forces based on this. You'd use symmetry, I suppose, so those would, but, but you could do that calculation, figure out what those external loads are. But yes.
Is this where about points start to get important too?
No, not yet, because anytime it's static, the about point you can choose anywhere you want. It's only, it has to do with velocities of points and it gets sort of complicated, but the moment equation just gets sort of messy if you're using points that are not the center of mass or a fixed point on the body. But everything all these terms that make it complicated go to zero anyways if it's static. And that's why you can choose any point you want as long as there's no accelerations.
And that's because the lever arms would be changing because you're not at the center of mass, right? It's not really because of that. It's because of there are all these velocity terms that end up making sort of cross terms when you do the derivation. And for these two about points, I mean, there's nothing, you can choose any about point you want. It's just that the dynamic equations get really ugly if you do that, unless it's at the center of mass or a fixed point. At those 2 points, a bunch of these cross terms cross out, and you get a nice simple form. And the nice simple form is the only one that you're going to get introduced to. So you could do it with any about point, but it's definitely not worth the hassle, Okay. Yeah.
So the F1s are canceling and the F2s are canceling, and that's why we're in static equilibrium?
Yeah, well, I mean, I guess, yeah. Don't worry about that too much. We're in static equilibrium because you're looking at this guy and he's flexing this pencil and it's not accelerating. What?
We haven't broken it yet.
Right.
Okay.
But we're trying to guess where it's going to break. Okay, so, but my point is, the reason that I'm drawing this picture is, based on the free body diagram, you would think there are 4 places where this could break. Here, 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 or here, because that's where the external forces are. But it doesn't break at the external forces. It's going to break somewhere in between the thumbs.
Is it like the average spot between them?
Why does pasta break multiple times?
Oh my God. That is literally a quantum physics problem. The pasta breaking thing. Like if you Google, why does pasta always break 3 times? You will go to recent physics research that to answer that question. So I am not going to answer that question. I don't know the answer to it, but that's like a really complicated question that is not answered by statics. So this is where it really breaks. Okay, so what is it that makes a thing break, if it isn't caused by these external loads? So what causes something to break?
Is there like a almost like a pivot point in the center where there's compression on the bottom half of the stick and then expansion or tension on the top half? Like it's pulling apart.
That is a thing that factors into it. Yes, you are right about that.
Like all
Um,
molecules are in tension or compression, and so it splits where like the average is.
That thing about tension and compression is on the path, but there's no like one single sentence answer I can give you, you know, like you'd have to go through this, calculate internal loads, then calculate stresses and strains, and then, you know, that's how you'd go through this process. It's sort of a long process. What makes something, what was I saying here? What makes something break? You know, that's the question. Like, what's going to make this thing break? Like maybe your first thought would be like, I'm going to draw a free body diagram and those external forces make it break. But then it doesn't break where those external forces are. So what are we looking for? Like, what is it for something to break? And the answer is, it's not the forces that outside things cause to the body. It's the forces that points in the body apply to other points in the body. Okay? It's the forces they have to apply to each other for it to stay in static equilibrium. And if you exceed, if the forces required for this thing to stay in static equilibrium that the left half applies to the right half exceed what the material can handle, then the thing breaks. It's like it's like if you're in a big circle of people holding hands, spinning around in a circle, and those forces are getting bigger and bigger. Eventually, it's going to break where the two people, wherever it breaks, can't hold on anymore. And that's what internal loads are about.
So you're,
Calculating how hard you have to hold on.
you're making the object break itself, pretty much?
For internal loads?
Yeah.
Well, we're just going to calculate at every point what's the load that has to be applied to that point by its surroundings. And then we're not going to get into the question of how you know if that's enough or too much or whatever, but we're just going to see what the process is of calculating those loads. Okay? So the surrounding material has to apply loads to a given point to maintain static equilibrium. Those are internal loads. So that's what we're going to be calculating. The body breaks when it can't support those required internal loads. Okay, so if you think of a body as a string of people holding hands, spinning in a circle, you might have measured people's grip strength before you started doing that. And you say, these two kids here can only support a load of 200 newtons or whatever, you know? And so then at that point, you can do the calculations to measure what grip is going to be required at a given speed. And then when you get to a speed where it says these two people are going to have to hold on at 250 newtons in order to keep this thing together, you say, like, that's a problem. That's where it's going to break. And that's the basic idea of what we're going to do here.
Problem or hilarious.
Yeah, exactly. Problem for them, hilarious for us.
We should do this as a class so they can visualize it better.
Yeah. Okay, so I'm going to do a simple example, and I want you to always remember that, so things are going to get more complicated with this stuff, but what we're doing is always a version of this example I'm going to do, and this example makes things pretty simple, okay? So let's say we have, let's say this is our free body diagram of our beam. Let's say we have 500 newtons down here, 500 here, and at the midpoint, 1,000 up. And we want to calculate the internal loads halfway between that 500 and that 1,000. Okay, so let's get some distances. Let's say these are both 0.25 meters. This is 0.5 meters, so the whole thing is 1 meter. And we want to calculate the loads applied to the left half by the right half. Okay, so how are we going to do that? Well, we are going to isolate, we're trying to figure out loads applied to the, I say half. Shoot, sorry, you got to erase that. Calculate the loads that are applied to the left of the red line. By the material to the right of the red line. Okay, so our free body diagram. We are going to isolate this much, and let's see. So notice that all this, okay, that light blue is part of the body, but it's not part of what we're isolating. So all this stuff that's in light blue isn't happening to our chosen, body, part of the body. The only things happening are 500 here. And now, think about mentally go around the boundary. Where else are the surroundings applying loads to this body?
There's a joint or whatever?
Well, the joint, so I've already, sort of, like any actual physical joints, I've already put them in the free body diagram here, so we don't have to worry about that. But we want to think about it as a fixed joint between the part that we're isolating and the material that we're not isolating. Okay, so what does that look like? So
you have a moment and you'll have a...
yeah, exactly. So we'll say that there's a full reaction force, R, and then there's a couple, I'll call it MR. Okay, and that's because this is a fixed joint. So Newton's second law says 0, -500 plus Rx, Ry is equal to zeros. So our reaction force is equal to 0, positive 500. And then our moment equation I'm going to put the about point here at the left end. Says, so first we know that we're adding on this moment MR. That part's easy. And then what about the moments produced by that force R? The X component isn't going to produce any moment because its line of action goes right through the about point. But the Y force is going to, so we're going to have plus or minus moment produced by Ry with a moment arm of 0.25, just because that's where I drew that red line. And that's equal to 0. If Ry was positive, would that rotate clockwise or counterclockwise around that about point? Counter, so we want the positive. And so now we can write this as Mr plus 0.25 times, well, we already know what Ry is. It's this. So plus 0.25 times 500. And so Mr is equal to negative 125 Newton meters. Okay, so what we calculated is the loads that the light blue material applies to the black material. Okay, so at that point along the, and I say point, because we're never going to be considering the thicknesses of these beams. But at that location along the beam, those are internal loads, okay? And if what's required for static equilibrium is more than that material can take, the material is going to break at that point. Okay? So now, here's another question, though. So we sort of calculated the internal loads at that point, kind of, right? But what do you think would happen if we phrased it differently? We said, we didn't say, what are the loads applied to the left half by the right, left part by the right part? What if instead we phrased it as what loads are applied to the right part by the left part? What do you think would happen to those internal loads?
Should be the same.
It's a Newton's third law pair. And so if instead you asked for the loads applied to the right by the left, you'd get R is equal to 0, negative 500. And Mr is equal to positive 125 Newton meters. That's not super satisfying. What we'd really like is just a way to have both of those two questions give the same answer, and we're just going to call those internal loads at a location. So we'd rather have just a single set of values that would be called the internal loads at that location. And so this is going to lead to kind of a funky new sign convention. And this sign convention is if you're going, so if the body you're isolating is this way, and the part you're not considering is like that, the default directions, the positive directions for these internal loads are this way for the horizontal force, and that's called the internal tension. This way for the vertical force, down. You wouldn't really expect that, but that's what it is. That's given the name V, and it's called a shear force. And then a couple this way that's called the bending moment. And tension. And if that tension value is negative, then it means the thing is in compression at that point, not tension. Okay, so how does this weird new sign convention fix anything? If you're going from the other side, all of these have the opposite directions. So if you're doing your analysis working from the other direction, a positive value of the tension is like that. The shear force is now up. And the bending moment is this way. So the sign convention itself, renaming T, V, and M instead of just using our vector values that we're used to for fixed joints, that doesn't fix the problem on its own. But the problem requires a new definition of what positive and negative are. And while people were at it, they chose this funky new sign convention, because why not,
Let's use V again.
What?
I said, let's use V again.
Yeah, right. Yeah, exactly. Well, in statics, you don't get a lot of V's, so.
Okay, that's good.
Yeah.
We're not dealing with a lot.
Yeah. Right, exactly. So yeah, blame Thermo for that. All right, well, let's do this calculation with this sign convention. Okay, so again, we're going to isolate this part. We're going to ignore this part. And that means we're going to ignore this force, this force. We're going to consider, come on. Okay, we're going to consider this force. And now we're replacing the reaction loads of a fixed joint that we're used to with this new way of expressing them, a horizontal force, a vertical force, and a couple. Newton's second law says 0, negative 500, plus T0. Now, this can get a little confusing, but remember to think of these vectors as a unit vector in the direction of the arrow times the variable. So a unit vector in the direction of that downward arrow is 0, negative 1. Multiply that by capital V, and this comes out to be 0, negative V. That's what the effect of drawing that arrow down is. And all that is equal to zeros. And so we can see that there's no tension at that point, and the shear force is equal to negative 500 newtons. And then the moment equation, I'm going to choose this as the about point again. So 500 doesn't produce a moment, but we do have m. If we had a positive value of v, applying a force downward, would that make this thing rotate clockwise or counterclockwise? Clockwise this time, so this is minus 0.25 v is equal to 0. And so m is equal to 0.25 times the v that we already calculated. So the bending moment is equal to negative 125 Newton meters. This time, with this sign convention, if we did it from the other side, you get the exact same values. And those are what we're going to call the internal loads at that location. Okay, so this new sign convention we chose took the ambiguity out of what do you mean by internal loads? Do you mean this material's force applied to this material or vice versa? Now we have it so that it'll be the same no matter how you calculate it, and we can just talk about internal loads at that point. Okay? Any questions about that? Okay, so when you start to get confused about how to approach something, if you remind yourself that we're really just sort of building on to this idea of isolating one piece of a body and figuring out the loads that the rest of it applies, you can sort out a lot of those problems. So this is a super simple problem, but this is the basis of everything we're going to do. And just remember that. Okay, that's all.